right, so we made alcohols. How are we going to make ethers? Surprise, surprise, we're going to use a bunch of reactions we already know about. To make ethers, we have to make sure we can make an alkoxide. This is an alkoxide. So the first type of reaction we have to think about is acid-base chemistry. So what I have up here is an alcohol reacting with H-. So before you look at the right side of this reaction, is H- a base or an acid? So you've decided it's a base, right? So we have to really, like, formal charge is just so important. So what does H- imply? H- implies that H has a lone pair of electrons, and in that case it would be a really strong base. How strong is it? Is it stronger or less strong than the O- over here? All right, do we have any quantitative values that would help us figure that out? Yeah, we should have all of our pKa values right up in our brain. So this is an acid-base equilibrium where this is acting as the base on this side, this is the conjugate base on this side, so we have an acid there and acid there. What's our pKa of an alcohol? 16. And what's our pKa? This is also on our pKa table. We should know the pKa of H2, and that is 35. So this is a much stronger acid than that, so the equilibrium will fly over to this side in an instant when you mix these two reactants. So that's going to quantitatively provide us with our O- alkoxide. So why do we need this at all? Well, we need a nucleophile to transform an alcohol into an ether. So what's the difference between this molecule and this molecule? Well, essentially it's this 3-carbon unit right there. So how are we going to put that 3-carbon unit onto this oxygen? Well, if we think about this disconnection, what's on this side, what's on that side, is oxygen our nucleophile or our electrophile? So the nucleophile loves nuclei. It brings the electrons. Is that side going to be the negative charge, or this side going to be the negative charge? And hopefully you're thinking, well, this is more electronegative. This is going to make more sense as a nucleophile. This would be our electrophile. And if that's the electrophile, we essentially are breaking this down into like O-, and then the positive charge on that carbon. But we can't have that exact molecule, right? We can't have this exact molecule because that molecule has a primary carbocation, and we can't have that. But what kind of carbocation equivalent would we have? We can't put a full partial positive on there, but we can put a partial positive on that position, and that would be if we had a halogen attached to that carbon. So essentially, if we reacted this with the alkyl halide, this is a strong nucleophile. The alkyl halide would be a really good electrophile. It really has that good leaving group on there. So that's the situation that we're going to do. We first have to make this alcohol a good nucleophile, and we do that through acid-base chemistry. We would just add sodium hydride to it. And remember, sodium hydride, sodium plus, H-, so we have a really strong base. Once we add reagent 1, the H- is going to grab that proton. Those electrons are going to go back to the oxygen. It already had 2 lone pairs, now it has 3. That's going to provide us, just with an acid-base step, our nucleophile, our alkoxide, our O-. Then we have to react that O- with something that has a partial positive right there, and we can just use an alkyl halide with those 3 carbons on it. That would do an SN2 reaction. So once we add the second reagent, that would provide the product. So that's how ethers are made. It's nothing really new here. The only new thing is that we're combining acid-base chemistry and then following that up with substitution chemistry. So that's kind of the new thing, is we're adding multiple steps. But this first step is something you know about, acid-base chemistry. The second step is something you know about, substitution chemistry. So that's kind of the only new part, but hopefully it all makes very good sense because you know both of those steps very well. Turns out that this ether synthesis was discovered by someone named Williamson, and just in the historical context of organic chemistry, this synthesis method of ethers is called the Williamson ether synthesis. So if anyone says Williamson ether synthesis, all they're really talking about is, oh, we're making an alcohol into a good nucleophile, and then we're mixing that nucleophile with an alkyl halide. So pretty straightforward stuff. So we're going to do this again. All right, so this is our first type of kind of synthesis question. So essentially we'd say, what is needed? There are multiple steps needed to make this from, we're starting with alcohols, and alkyl halides. And you have any halides. And you have any inorganic reagents you'd want, such as acids or bases. How do we make ethers? So if you're feeling brave, just draw out your synthesis right now. You don't need anything else from me. You already know how to do this. All right, you already did that. For those of you that aren't feeling as confident, what can we do? We can either break this at that position, we'll call that breakage A, but we could also break it this side, right? This would be breakage B. So just like what we did earlier on this page of the course packet, one side of this is going to be the alkyl halide, the other side is going to be the alcohol. So breakage A, this side becomes the alcohol, that's the alkyl halide. Breakage B, that side's the alcohol, or this side's the alcohol. So yeah, let's write those out. So A would have this be the alkyl halide, and we would use this alcohol. B, we would have this as our alcohol, and this as our alkyl halide. So what's the better method? At this point, it probably makes sense for you guys to pick one and then draw the same stuff. So essentially we'd have the alcohol, ROH, 2 boxes, 1, 2, and then we have our product. So which option is the better? Is breakage A better or breakage B better? So you've drawn that out, you've thought about it some. So one of these is going to produce an unwanted side product. What does substitution compete with? Yeah, substitution competes with elimination reaction. So are either of these going to have more of the elimination pathway than the other? Well, B would have the O- reacting with a primary alkyl halide. A would have the O- reacting with a secondary alkyl halide. Yeah, and secondary alkyl halides with strong nucleophiles, this combination does a mixture of SN2 and E2. So this is not as ideal of a method. The better method is method B. So what would that look like? So I'm just going to erase those things. So essentially, we'd take our alcohol for method B. We'd say first we're going to treat that with our strong base, sodium hydride. That would produce the alkoxide that looks like this. And then secondly, we would add our electrophile. That would be that 3-carbon chain with the chlorine or bromine or iodine, and that would do a substitution reaction. So that is the best method of Williamson ether synthesis. Will breakage A still make some product? Of course it will, but it will make less product, and what we want is the highest yielding option, and that would be this breakage B that we just talked through. So that's the only kind of challenge of the Williamson ether synthesis is you may have two different ways that you can break the molecule apart. If it is an unsymmetrical ether here, like it is here, in that case, you're going to have to make the right decision about which side you would break it apart with.